Okay guys, we are going to do the section 1 notes. So there is a little bit of math in this, so once again, if you are having any issues, just ask me tomorrow or tell me what's going on tomorrow and I will help you out. Just let me get this on the board. There we go. Okay, so the first thing we're going to talk about is law of conservation of mass, which we saw in last chapter, in chapter 7 a little bit, but they don't talk about it until chapter 8. The reason we have to balance equations like we saw in the previous chapter was because we cannot create or destroy matter. So that's what you're going to write here. You can't, I always say create or destroy, not destroy. Create or destroy matter. Alright, so that means that, like, what we have here is what we have. Now, it may change. Like, I have, we have paper, which is carbon, hydrogen, and oxygen, and when I burn it, I get some CO2, some H2O vapor. It changes, but I can't start out with 2 oxygen molecules and end up with 4. Or vice versa, I can't start out with 4 and then somehow only end up with 2. We can't create or destroy matter, which is why we balance. All right, so let's watch this YouTube video.
In this video, we examine the historical and present-day significance of the law of conservation of mass. In the 18th century, scientists thought that when things burn, a substance called phlogiston came out of them. Then, experiments in closed vessels where substances could be accurately weighed began to help early scientists, such as Lavoisier, understand that when things burn, oxygen is added. He realized that matter could be changed but not destroyed. In 1789, he established the law of conservation of mass. In chemical reactions, no matter is lost or gained. These experiments on combining weights also showed that elements always combined in fixed ratios, the law of definite proportions and constant composition. And they led Dalton to publish his atomic theory in 1808. Modern chemistry had started. By mid-19th century, only half the elements had been discovered, but enough to enable Mendeleev to produce his famous periodic table. That was in 1869. Chemical equations began to be written as we now know them from about this time. For example, the burning of magnesium. This needs balancing. When we balance an equation, we are simply obeying the law of conservation of mass. All the atoms in the reactants must be accounted for in the products. It's easy to see this if we draw out the atoms, rearranging themselves to form the products. You can see clearly that no atoms are gained or lost during a reaction, so the mass is conserved. Here is another example, a reaction you'll see every time you use a gas cooker which uses natural gas. But is this reaction balanced? Pause the video and count the carbon, hydrogen, and oxygen atoms on each side. It is easier to count if we draw out the molecules as models. Carbon, 1 each side, oxygen, 2 to start with, but now 3, hydrogen, 4 to start with, but now only 2. To balance the hydrogens, we need to add 2 more hydrogens on the right. To do this, we add another water molecule. Pause and count. Is it balanced now? Well, the carbon and the hydrogen balance, but we have 4 oxygens in the product, but only 2 in the reactants. So we add another oxygen molecule to the reactants. Now we have conserved mass. In summary, the law of conservation of mass is simply saying that during chemical change there is no loss or gain of atoms. It is for this reason that we always balance chemical equations. Until you are really familiar with using formulae, it's easier to draw out the molecules as models to enable you to account for all the atoms.
so we've been doing that with the balancing of stuff. I'm gonna erase this. If I'm ever going too fast, just pause it, go back to where you need to be. All right, so looking at this, we're counting atoms like we did. And it wants to know how many hydrogens are on my reactant side. Well, I know the reactant side is on the left-hand side of that arrow. So if you look at hydrogens, there are 2. How many chlorines, or 2, you could say 2 moles of hydrogen. How many chlorines are on the reactant side? There are 2 moles of chlorine, because I'm asking for just Cl. I'm not asking Cl2. So what I'm asking here, it's a little bit different, and I don't want this to get confusing. If I asked you how many moles of hydrogen gas, how many moles of H2, there are 1, okay? If I ask you how many moles of hydrogen, that is the same thing as saying how many hydrogens are there, and there are 2. Okay, so it is a little bit different here. So then on the product side, I'm looking on the right-hand side of my arrow. It wants to know how many moles of hydrogen. There are 2. Remember, it's the same thing as me saying how many hydrogens are there. Same thing here, how many chlorines are there? There are 2 moles of chlorine, right? There's my 2 hydrogens, my 2 chlorines. All right, now I'm going to do the weights, right? If this should be equal, right? I've got 2 moles of hydrogen, 2 moles of chlorine, and on the other side I've got 2 moles of hydrogen, 2 moles of chlorine. So if I'm getting the weights here, I have 2 hydrogens, which are going to be 2 grams. I have 2 chlorines, which are going to be 71 grams. Now that is taking, remember, I'm weird. I can't leave that 0.5 off there. I don't round chlorine. So 35.5 times 2, that's going to be 71. So this is 73 grams all together on my reactant side. If you look over here, it's going to be the same thing. Hydrogen is 1 gram, but there are 2 of them. My chlorines, it's the same thing, 71 grams. So this is going to be 73 also. So really, this is what we should see. My reactants should equal my product because I cannot create or destroy matter. So it may look a little bit different on each side of that equation from my reactants to products, but the mass should be the same. All right, so then if we were in class together right now, I'd be like, guys, if we saw this and you were on the phone with somebody, how would you read this to them? I wouldn't say 4Fe plus 3O2. You could say that, but I want to know what's the correct way to read this. So I would ask you guys that, and I might give you a second here. But the way I would read this I could say 4Fe, but I want it the proper way. I'm going to say 4 moles of Fe, or iron, you could say, react. Now this plus sign is saying that they're added together, so it's reacting. React with 3 moles of oxygen gas. I'm just going to put the 3O2. Now here's my arrow. That means it's producing. So to produce, and there's that 2 moles of Fe2O3. All right, so if I were just reading this, 4 moles of iron react with 3 moles of oxygen gas, or O2, to produce 2 moles of iron oxide, or Fe2O3. All right, so that's how you would read that. So using the equation above as a recipe, imagine that recipe, kind of like we did with the s'mores pops. If I have 4 moles of iron, how many oxygens do I have? So if I have 4 of these, I must have 3 of these. And if I don't have 3, if I only have 2, then this reaction will not take place. It cannot happen, because you would never be able to conserve mass. So you have to have 3 of these. If I have 4 irons and 2 moles of oxygen gas, nothing will happen, because they cannot rearrange themselves into a way that makes them all happy and all content with their valence electrons, so it won't happen. So if I have 4 moles of iron, I want to know how many Fe2O3s do I have? It will be 2. Okay, if I have 4 moles of iron and 3 moles of oxygen, I will get 2 moles of this every time. Now, if I doubled everything, if I said I have 8 moles of iron and 6 moles of oxygen gas, well, I'm going to end up with 4 moles of iron oxide. So it's just you have to conserve. But if I have, oh gosh, 4 moles of iron and 1 mole of oxygen gas, I will not get 2 moles of iron oxide. It's not going to happen. All right, so we're going to talk mole-to-mole factors because we use these when we do our math. So the mole-to-mole factors are using these numbers in the front right here. So when I talk about this, I'm talking about if I give you a problem and I do these parentheses like this, like what could go on bottom, what goes on top. And it always depends on what you have here, right? If I have moles of iron here, then I'm going to put moles of iron on bottom. If I had moles of O2 here, then moles of O2 would go on bottom, right? So it just depends. So that's why I'm going to write a bunch of different ones here. So here's one of them. I'm going to use my iron. I'm going to put, 4 moles of iron. And when I have 4 moles of iron, I could have 3 moles of oxygen. Right? I could write it that way, or I could write it with my 3 moles of oxygen on bottom and my 4 moles of iron on top. Remember, it all just depends, what do I have out here? What do I have out here? That's what depends what goes on bottom. All right, so another one that I could do is I could compare my iron to my product, this right here. So here's one. I could say, okay, well, I'm going to have 4 moles of iron, and that's going to go with 2 moles of Fe2O3 iron oxide. Okay, I could write it like that. Now, if I gave you a problem that started you with iron, that's what I would write down. Or if I gave you a problem that said, hey, you created 5 moles of iron oxide, how much iron is that? So that one would look like this. I would put my iron oxide on bottom. And I would put my moles of iron on top. Okay, so that's another mole-to-mole factor. We have one more. The last one we could do is comparing oxygen to iron oxide. So when I do that, it could be 3 moles of oxygen gas compared to 2 moles of iron oxide. Now, I would use this style of problem if I were to say, hey, you have 6 moles of oxygen. How much iron oxide does that give you? I would use this. But if I gave you a problem that said, you produced 8 moles of iron oxide, how much oxygen did you have? Then I would use this style. I would put 2 moles of iron oxide on bottom, and I would put my 3 moles of oxygen on top. Okay, so these are all mole-to-moles. And when I do a mole-to-mole problem, oh, I believe I said this to you last year. I'm getting confused now with what I did in Chemistry 2 versus Chemistry 1, and I had you guys in Chemistry 1 last year. Mole-to-mole, I will always use my reaction up here. I'm using this to get those numbers anytime I have to do a mole-to-mole. Okay, so let's look then at the next page. We're going to do a learning check, and we're going to do a few calculations with it. All right, so let's look at this learning check. It says, consider the following equation and a mole factor for hydrogen and nitrogen. So I'm looking for hydrogen and nitrogen. I'm looking here and here. So I know for every 3 moles of hydrogen gas, I have 1 mole of nitrogen gas. So this is not correct because there's 1 hydrogen, and I know that's not true. Here, 3 to 1, that one works. This one says there's only 2 hydrogens, and there's not, so that one does not work. All right, B, a mole factor for NH3 and hydrogen. So now I'm looking at hydrogen and NH3. This has 1 mole of hydrogen, and that is not what it tells us in our equation, so that's not right. 2 moles of NH3, that's what I have here, 3 moles of hydrogen, so this one's right. Let's make sure this one, 3 moles of N2. Well, it's not even asking for N2, so that one's not right. All right, so now let's look at some calculations using these then. Okay, so that was just getting us set up to figure out like what are going to go in my conversions. it says you need 4, it's what we had up there, 4 iron, 4 moles of iron react with 3 moles of oxygen to produce 2 moles of iron oxide. So here I'm saying, how many moles are you going to produce if can form from 3 moles of oxygen? Well, we just saw this. If I have 3 moles of oxygen, I am producing 2 of these, right? 2 moles of Fe2O3. There's no real math I had to do with that. It gave me 3 moles of this, which is what I'm starting with, so I just have to look up here and find that. They want to know then, all right, so if that's 3, how many moles of iron oxide are you going to make if I have 6 moles? So now instead of a 3, this would be 6. Well, I just doubled it, so guess what? I'm just going to double this also. So that's going to be 4. Now I'm going to show you how you could set that up if you're going to know, because eventually we're not going to be working with nice, easy numbers like that. So if I were setting this up as a math problem, I would say, okay, they gave me 6 moles of oxygen. Always write down what they give me. I'm going to do my parentheses, moles of O2, go down here, and I'm like, okay, what are they asking? They're asking for moles of Fe2O3. Then I use my equation. Anytime I have a mole to a mole, I'm using that equation, and it tells me I have 3 oxygens and 2 iron oxides. So I would take 6 times 2, which is 12, and I would divide that by 3, and that gives me 4 moles, right? So that's how you do the math you did that. So then it says, okay, well, how many grams of Fe2O3 is that? So if I look at that, I've got, okay, so I've got 4 moles. It's like saying 4 Fe2O3. So that's really 8 irons. So I've got 8 irons, which iron is 56 if you round up. So I've got 56 times 8. Plus my oxygen is 16, and I have 12 of those. When you add all that up, it should give you 640 grams. Okay? So number 2, I wrote it off to the side here, but it's like, how did you figure out number 2? What type of math did you do? This should go right here. All right, so then let's do the learning check. And if you want, pause the video, see if you can figure this out, and then unpause it, and I will, all I'm getting ready to do it right now, and I do the work with you. But if you're not sure and you want extra practice, just go ahead and listen to me and follow along. So this says how many moles of iron are needed to react with 12 moles of oxygen. So I'm always going to start off with writing down what they give me. I'm going to do my parentheses. I always know, if I'm not, without even reading the question, I can't remember right now what I'm even looking for. I know that this, though, is going to go on bottom. All right, so now I'm going to read my question again and figure out what they want. They want how many moles of iron. So that's what I'm going to put on top. Mole to mole, use this reaction. So I'm using 4 moles of iron, and my O2 is 3. So I'm going to take 12 times 4 divided by 3. Now once again, you could take 12 divided by 3 times 4. It doesn't matter which order you do it in. But when you do that, you're going to see 16 moles of iron. Okay, so what this is saying is if I have 12 moles of oxygen, I'm going to need 16 moles of iron for all that to work out. All right, so well, let's go ahead and do this part right here. It says if 1 mole of iron is 56 grams, how many grams is in this answer right here? So I know 1 mole equals 56, so how many is 16 moles? Well, if you think about that, that's going to be 16 times 56, okay? Or, if you're trying to set this up, I have 16 moles of iron, and I want to know how much that weighs. Well, how much does that weigh? Well, I know moles of iron go on bottom, grams of iron right here. I know from the periodic table, and remember, anytime I do a gram and mole, I'm always using that periodic table. It's always 1 mole of iron weighs 56. And look, that will show you I'm going to take 16 times 56. That is 896 grams. We're going to end there because I'm not going to get into the 2 steps or the possible 3 steps that we can get into. So we're going to end right there, just doing these mole-to-moles. Your worksheet today is for participation, so just try it out. At least always write down what they give you, and then when you go to set up your equation, what they give you, that unit is going to go on bottom. So at least you can maybe get started on that. Try your best. Tomorrow I'll be back and we'll check the worksheet for participation, so make sure it's done. If you have questions, I'll answer them tomorrow, okay? You guys have a great rest of your day, and I will see you later. Bye.